Hello and welcome to Colloquium Lecture 3. I'm Ruth Charney, President of the American Mathematical Society, and I will be moderating this session. My apologies for the technical glitches we encountered at yesterday's Colloquium Lectures. Fingers crossed for this final lecture today. Our speaker for Lecture 3 is again Karen Smith, the William Fulton Professor of Mathematics at the University of Michigan. Professor Smith is highly regarded for her outstanding research and has also served as an inspiring role model for many women in the field. This series of lectures is about understanding and measuring singularities in algebraic geometry. I do hope that many of you were able to attend her two previous lectures, which, by the way, were terrific. Before we start, let me remind you that if you have questions for the speaker, I would ask that you please put them in the Q&A, not the chat. I will be reading questions from the Q&A at the end of the talk. So today's talk is entitled Extremal Singularities. Please welcome Professor Karen Smith for Colloquium Lecture number 3.
Hi, thank you, Ruth, for that introduction, and welcome everybody to the third and final talk on singularities in algebraic geometry. I am going to try to share my screen. Are you seeing it okay? Okay. I'll make it full screen. Does that look good? All right. By the way, I noticed on the slides that were showing before the talk when you were waiting, there was a typo in my title. I'm not talking about external singularities, but extremal singularities. And I'll explain what that means as we go along. But I just wanted to point that out in case anyone was confused. Okay, so let's get started. And I also wanted to say, because I didn't get to finish exactly what I was saying last time, and you guys missed an important open question at the end. If anybody would like the slides, you can shoot me an email and I will share them. Okay, no, it is not advancing. There it goes. Okay. So let's begin by remembering what we were talking about. So for this, I want you to fix your favorite field. So for many of you, that might be the field of real numbers. For me, if you're like me, it might be something like the algebraic closure of the field of P elements. But fix a field, and once you fixed a field, we can start talking about varieties and hypersurfaces over that field. So remember, a hypersurface is the zero set of one polynomial. So we have to think in a particular space, in an n space. We have a polynomial and n variables over that field. So what you'll get is a geometric object in the n-dimensional space over that field. So if our field were R, for example, and we picked the polynomial x squared plus y squared minus z squared, the zero set of this, the place where this polynomial vanishes, is exactly this yellow cone in 3D. And similarly, this apple is the zero set of a different polynomial in 3 variables, looking at it as a real polynomial, so the picture is in R3. So remember, if you picked something like R, you may not be seeing all the zeros of your polynomial, and for that reason, algebraic geometers usually like to work over an algebraically closed field, such as C. There are more points on these things that live in C, and that's where we see all the zeros of the polynomial. But it doesn't matter too much to get an idea what's going on, although technically speaking, some of the theorems I say require an algebraically closed field. Okay, so what we were talking about last time in the previous 2 talks was singularities of these kind of hypersurfaces, or varieties more generally, which would mean it was defined by more polynomials. This cone has a singular point here at the origin, and this apple also has a singular point at the origin. And in fact, if I want to focus attention on a particular point of my hypersurface, like this point for some reason, I can always choose my coordinates and put my origin there if I want to. So throughout this talk, when I'm talking about a point or a singularity on a hypersurface, I'm always going to be thinking about it as being the origin. I'm always going to choose coordinates, so it's the origin. So what we did in the last talk, in talk 2, and you don't need to remember the details of that at all, I will tell you exactly what you need to know about it. What we did in the last talk is we came up with a numerical way to measure the singularities of a singular point, to measure how bad it is. So we could assign a number to every point on our hypersurface. If we pick a smooth point on the hypersurface, the singularity index is going to be 1. And if we pick a singular point, like the center of this apple, where we have a singularity here at the origin, the singularity index will be most likely smaller, because the smaller the singularity index is, the more singular or more nasty the singularity is. So we came up with precise ways to do this last time. You don't need to remember the details, but I do want to point out and remind you that when we were dealing with a variety or a hypersurface over a field such as R or C, or a place where we could do analysis, we used the tools of analysis, epsilon neighborhoods, balls, integration. We used analysis in order to define a number associated to each point, which we called the log canonical threshold. And for some fields where we couldn't do analysis, such as a field of finite elements or the algebraic closure of a field of finitely many elements, we needed a different tool to define this singularity index. And that was called the, well, the name of that singularity index was called the F-pure threshold. And the way we defined it was by using this Frobenius map or Pieth power map. So none of that needs to be recalled for this talk. The only thing you really need to know in order to, why is this not advancing? Oh, there it goes. The only thing you really need to know to understand what I want to tell you about today is that we can define this singularity index, and I'm just going to call it the singularity index today, instead of adding all those extra syllables and making it depend on the field every time. I'm just going to call it the singularity index. We have this singularity index that we can associate to every point on our hypersurface, and that number will always be a positive number. It'll be less than or equal to 1. If I'm looking at a smooth point, it will be equal to 1. And if I'm looking at a singular point, it will probably be small. The more singular the point, the smaller it will be. And so here's 2 complex hypersurfaces. I've drawn them as if they're real, of course. And the origin is a singular point on each of them. And we see that the singularity index is larger for the cusp on the left than it is for the cusp on the right. And the reason is that the cusp on the right is more singular. It has a smaller singularity index because it's more singular. And intuitively, you can see it's more singular because it's just a sharper cusp. And we talked a little bit about other ways you could think about it being more singular. But for this talk today, I want you to keep in mind the singular index is a numerical way to measure the singularities. And we're going to see what we can do with that. So now one thing I also want to remind you about is that the field does matter for the singularity index. If I have a polynomial like that cusp, the y squared minus x cubed, which defines this nice cusp here, it's drawn in the real R2 plane here. The polynomial makes sense over any field, right? Because every field has a 1 and a minus 1 in it. In some fields, like a field of characteristic 2, 1 and minus 1 are the same. That's actually my favorite field because you can't make a sign error in characteristic 2. But in any case, this polynomial could be interpreted over any field. And so we can look at the geometric object obtained by looking at the zeros of this polynomial in K2 for any field K. Each choice of K gives us a different hypersurface. We always draw it as if it's R, because that's the best we humans can do. But in all these cases, these are different geometric objects. They all are very similar. They're one-dimensional algebraic curves. They all have an isolated singularity at the origin. Isolated means that it's by itself, right? If I move a little bit away, it's there next to a smooth point on either side. So for all these different choices of K that we might make, the singularity index depends on K. So this example I did mention last time, I just wanted to remind you of that fact. And here I've listed some of these singularity indices, what we get in different fields. Any field of characteristic 2 will get a half. Any field of characteristic 3 will get 2/3, and so forth. Over the complex numbers, we'll get 5, 6. And notice that's the biggest number of all of these on the list. In some characteristics P, but not all characteristics P, this curve is more singular. And this curve is most singular where we have the smallest singularity index over a field of characteristic 2. And it's kind of an interesting exercise you might want to think about. Why is this thing more singular in characteristic 2? And if you remember the way we defined the singular locus or a singular point as one where we can't define a tangent plane, and we said that had to do with the derivatives vanishing. Notice the y derivative of this is 2 times y, right? And 2 times y is 0 always in characteristic 2. So we have sort of extra vanishing of derivatives in characteristic 2 that we wouldn't necessarily expect, for example, over the complex numbers or even over any other field, like a field of characteristic 7 or so forth. So that's one way in which we can imagine that this geometric object might be nastier in characteristic 2. But this number also tells us other interesting things about the singularity in characteristic 2. Okay, so that was a little reminder of what the singularity index is. Again, the definition was given earlier. It depended on the field, but it's not important for this talk. You just need to know that it's a number that tells us how singular things are. And this leads to the topic that I want to talk about today, which is there a worst singularity? We have a number assigned to every singular point. Is there a smallest one? The smallest one would be the most singular thing, right? And we do have a lower bound on the singularity index because we said, remember, it was a number, positive number, less than or equal to 1. So 0 is a lower bound on the singularity index always. But is there a positive lower bound? Maybe the lowest it can be is 1,000,000, a 1/1,000,000th. Maybe the lowest the singularity index could be is 1,000,000. And if that's the case, whatever curve has singularity index 1,000,000 would be the most singular one, or whatever hypersurface, a point on a hypersurface with that lowest possible index would be somehow the most possible singular, the worst singular point we could find. So that's the question I want to discuss today. If we could prove a sharp lower bound on the singularity index, we could find hypersurfaces achieving it, we would want to call that hypersurface, that singular point on the hypersurface, an extremal singularity. It's extreme in the sense that it's the nastiest, it has the smallest singularity index. So that's the question I want to address today. And this has a beautiful answer. I'm really happy with this project. I'll tell you more about the history of the project, but it has a nice algebraic and geometric answer. So asking again, is there a smallest possible singularity index? The answer posed to that very naive question is obviously no. So it's too naively stated. We have to restate it better. But let me give you an example to convince you that the singularity index is definitely not bounded below in general. If I just take d distinct lines in the plane, I could take them in the real plane even, but because I'm an algebraic geometer, I like algebraically closed fields better where I see all the points. So I'm thinking of d distinct complex lines in the plane, then they all cross at one point, which is the origin. because we've chosen our coordinates that way. It's not too hard to prove that the singularity index of this singular point at the origin is 2 over d. So if I make d larger, I take more lines crossing, I get a more singular curve. And it makes sense, right? It's harder to, the more lines I put in there, the more trouble I'm going to have to choose one tangent line at the point, which would be the definition of a smooth point on a curve. So there's no lower bound on the singularity index in general, but you might be thinking, well, is she cheating? She took d different hypersurfaces and took a union of them. This variety, this hypersurface here, has d different components. It's not irreducible. What if we restrict to irreducible varieties, or irreducible hypersurfaces, one that only have one component? Well, it's not true in this case either. And let me give you, it's harder to come up with examples, of course, but here's an interesting one. All of these rose curves you've probably seen before listed in or written down in polar coordinates. Here is the formula for the curves I produced on the left side here. These curves are all algebraic curves. I'm not telling you the particular polynomials here, but there is a polynomial in 2 variables whose zero set is exactly these curves. And like I said, it's much easier to write these down in polar coordinates. The polynomials are quite long and complicated, but they're not too bad. You could actually work it out using the multiple angle formula for cosine. And what we see is that the singularity index of these singularities, these are the origin, these centers of these flowers are the most singular point of each one of those flowers. And the singularity index here is going to be getting smaller and smaller and smaller as well, with increasing numbers of petals and also tangencies of petals. So some of these petals are tangent to other ones, and that's going to be making it more singular when that happens as well, lowering the singularity index. So for example, if I just take a odd integer here, I would just get a nice Q-petaled flower. If the petals wouldn't be tangent in that case, and the singularity index is 2 over Q. So we can see, even just looking at odd petaled flowers, the singularity index is not bounded below by a positive number. These, as Q gets large, approach 0. But what's happening here as well is that the order of these polynomials defining these petaled flowers here, these roses, are getting also larger and larger with increasing numbers of tangencies and petals. And so we are led to restrict the question again and fix the order. So let me remind you what the order of a hypersurface is. This is the same as the order of vanishing of the polynomial at the origin, where we're fixing our attention. And the order of a hypersurface at the origin is simply the degree of the lowest degree term appearing in the polynomial defining the hypersurface. So our 5-petaled rose, for example, if I look at its equation, so here I've written out the equation, hopefully correctly. It's a computation. I do know it's 5, so it's close enough. What we see is the lowest order part, the lowest degree part of that equation. We have some degree 6 stuff on this side. We have some degree 5 stuff on this side. And so the order is 5. And so this is an example of order. We talked about this last time. But as we just observed, the singularity index will not be bounded if I allow the order to be unbounded. And so I now want to fix the order of my singularity and ask, is there a lower bound on the singularity index if I fix the order to be some number? Okay, so this is where we can start answering questions, and I'm going to pose them one more time clearly these are the things I'm going to talk about in my talk today. So we are going to consider hypersurface singularities. The singular point we're focusing on is the origin, and we're going to fix the order when we're looking at it. Fixing the order to be D, is there a lower bound on the singularity index we can give in terms of D? If so, not a positive lower bound. We know 0 is a lower bound, but we want a meaningful one that we can use. Is it sharp? Can we find a sharp lower bound so that there's an actual polynomial of order D that achieves that lowest possible singularities? If there is, that's an extremal singularity, and then we want to understand it from an algebraic and a geometric point of view. So here are just pictures of 3 order 2 singular hypersurfaces. You can see the singularities looking like they're getting worse as we go from left to right. Is there a worst possible singularity? That's the question. All right, so to answer this precisely, I need to introduce you to cone singularities. This is a very natural thing. You can just do in any geometric setting. You really don't need algebraic geometry per se. If I take any set in my n-dimensional space, I can construct a cone over that set. So what I do is I embed my n-dimensional space. Down here is a cartoon of an n-dimensional space Kn with a set X, this donut in it. And then I embed X, my Kn, my n-dimensional space into an n+1 dimensional space. And then I pick a point, any point in the n+1 dimensional space, but not in the n-dimensional space we started with. That's going to be our vertex. I'm going to call it 0. And then I draw all the lines through that fixed point to any point at all on X. So you can see this is going to make a new shape. It's going to be in n+1 space instead of in n space. And that's called the cone over X. So if I happen to start with an algebraic variety X in the n-dimensional space, the cone will also be an algebraic variety. It'll be an algebraic variety in the n+1 dimensional space. And if I happen to pick a hypersurface in the n-dimensional space, the cone will be also a hypersurface in the larger dimensional space. The cone will have dimension 1 larger, which is easy to visualize since I added these lines to every point of X. And if X happened to have been a smooth hypersurface or variety, then this cone will have an isolated singularity at the vertex. So these are very interesting singularities. They're not the only kinds of singularities, but given a singularity, I can always build the cone over it, and the cone over it will be at least as singular, it turns out. So we sort of expect we might find the worst possible singularities among cones. And now, one thing I want to point out is if I had started with a hypersurface and I built the cone over it, that will also be a hypersurface. It will be defined by a homogeneous polynomial. So let me remind you, I think everyone knows what a homogeneous polynomial is, but just in case, I put down 2 examples, a homogeneous polynomial of degree 3 and a non-homogeneous polynomial of order 3 and degree 17. Notice for a homogeneous polynomial, the degree is exactly the same as the order, because there's only, all terms have the same degree. And so the degree of the lowest degree term is the same as the degree of the polynomial. In other words, the degree and the order are the same for homogeneous polynomials. So we said that if I started with a variety in or a hypersurface in some n-dimensional space, like for example, a circle here in the 2-dimensional space, and built the cone over it, I get this homogenized polynomial. This is a homogenization of the equation of the circle. Now, the converse is also true. If I take any homogeneous polynomial of some degree in n variables, maybe I should use n+1 variables here, I will get a cone-shaped object in the sense that if I pick a point, any point on the 0 set of that homogeneous polynomial, then the entire line through that point and the origin will also be on the hypersurface. So it will always have a cone-like shape. So from the point of view in the very first lecture where I said every geometric concept in algebraic geometry has a corresponding algebraic equivalent, cone singularities correspond to homogeneous polynomials. And this is an example here, our favorite cone, the actual cone over, it's a cone over a circle. Okay. So for cone singularities, we can completely answer this question. And this is, I think, really interesting. For cone singularities, we can give a sharp lower bound on the singularity index in terms of the order of the singularity. So in terms of the degree of the homogeneous polynomial defining that cone singularity. And not only that, but we can classify the singularities. We can give a nice algebraic description of those extremal singularities, the ones achieving this minimal singularity index. And we can basically list them out, give you a list of all of them. So this theorem started, the picture here, it started in a Women in Commutative Algebra workshop at the Banff Research Station. And this is a picture taken from that day, or from that event, which was really inspirational to have a team of really smart people to work with. And we got started on this theorem then. And ironically, I think the pandemic helped us because at least I didn't have as much going on as I usually do. And I think the same was true for most of us who don't have kids. I know if you have kids, it's a hard thing. I have kids, but they were old enough to handle themselves mostly. And so we spent a lot of time on Zoom proving these theorems. Now this theorem here is stated sort of informally. I'm going to state it more carefully on the next page. So this is now a precise statement. I'm taking my homogeneous polynomial. Remember, that's defining this cone singularity. And then the singularity index of the vertex of the cone is always going to be bounded by this fraction 1 over the degree minus 1, or the order minus 1. Very simple bound. Very simple bound. And we can say exactly when equality holds. Equality holds only if the field is characteristic P, and only if the polynomial G, this homogeneous polynomial, has this very special form. So for example, the theorem says if I'm restricting myself to degree 4 quartic hypersurfaces, then all degree 4 cone singularities, order 4 cone singularities, have to have singularity index at least a third, and the ones that have that minimal possible singularity index of 1/3 are very special. They're only ones where the characteristic is 3, right? Because in order to have degree 4 of G, we need to have P is 3, E is 1. And so this is like x1 to the 3rd times some linear polynomial and so forth. Very special. Now, it's not surprising, it shouldn't be surprising that this minimal singularity happens only in characteristic P, because we talked about earlier how the singularity indexing for the complex curves bounds above always the singularity index for the corresponding mod P reductions of the curve. All right, so let's give an example. Let's think about homogeneous cubic polynomials in 3 variables. So many of you will be familiar with this as the homogeneous equation of an elliptic curve. And I'm not sure if you heard me talk about this yesterday, because I'm not sure when the lecture ended. But one of the things I mentioned is that these singularity indices have been computed for the homogeneous equations of elliptic curves. And here's the formula. We see that It doesn't really matter if you know exactly what ordinary elliptic curve or supersingular elliptic curve means, but supersingularity, ironically, there's many definitions for it, but it doesn't really have to do with singularities per se, because all elliptic curves here are smooth, but they have other properties that make them supersingular, and their cones over, what we're proving is the cones over elliptic curve are literally supersingular. Their singularity index is smaller than the expected one, the one you get most of the time, the one that you get over C. And what you also see when you look at this formula for the singularity index here is that the smallest the singularity index can be for any cubic curve in 3 variables, according to our theorem, is 1/2, but also according to this computation is 1/2, because the case where P is 2 is what's giving us 1/2 here. And so our theorem is saying equality holds if and only if the field is characteristic 2 and the equation has this very special form. And so here's just one example of a specific homogeneous equation in 3 variables of degree 3, which is an extremal singularity, if we're in characteristic 2. Okay, so that's our theorem. Let me point out quickly that, as I already mentioned, we never expect to see the most extreme singularities over the complex numbers, because things can only be worse in characteristic P. And in fact, there are theorems that quantify this difference. Over the complex numbers, there's a theorem that gives a lower bound for a homogeneous polynomial of degree D, so a cone singularity of D, but now not allowing all fields, only allowing the complex numbers. And if we only allow the complex numbers and ask what is the most singular a cone singularity of order D can be, we have an answer. The specific answer is not super important, but it's also quite simple. It's just in terms of the degree and the codimension of the singular set. So the codimension means the ambient variety dimension minus the dimension of the singular set. Notice in characteristic P, that didn't matter what the dimension of the singular set was. And moreover, these authors, so this is Tommaso de Fernix, Lorenzine, and Richard Mastada, they have a condition under which we would have inequality as well. One of the conditions is if you have an isolated singularity, it always holds this bound that all the singularities are extremal. They achieve the minimal bound, the lower bound. I mean, they all have. We know what it's not that big of a theorem in that case, because we know exactly what the log canonical threshold is, or the singularity index is always in that case anyway. But what I want to attract your attention to is that our lower bound is 1 over D minus 1, and that's achieved by some hypersurfaces. And the lower bound in characteristic 0, or over the complex numbers, is this much bigger number in general. N is the dimension of the space the thing sits in, so it's got to be at least 2, otherwise we're just talking about points, nothing singular going on. And so we see that this, as D gets large especially, our singularities, our lower bound is much smaller. And again, the interesting part is that it's sharp. It's really achieved by certain curves or certain hypersurfaces, but only in characteristic P. Okay, so let me now describe all of the extremal singularities, extremal cone singularities. So this is really just another way to state the theorem that we proved or started proving in Banff. And at the top of the screen here, I'm repeating our lower bound on the singularity index. And I'm pointing out that the shape of the very special polynomials for which the corresponding hypersurface has an extremal singularity can be put into this matrix factorization form. So what I mean is our G can be written as the product of 3 matrices Here I have a 1 by n matrix with variables in it. Here I have an n by n matrix with entries in the fields, so some entries that are scalars. And then I have an n by 1 matrix, again, of the variables. When I multiply these three matrices together, I have a 1 by 1 matrix, which of course involves the variables. That is the form of G. So these are exactly the polynomials that achieve that minimal possible singularity index, which is the F pure threshold, if you remember what it was called in characteristic P from yesterday's talk. I want to also point out something kind of for fun and interest. I've stated this theorem on this page for D is larger than or equal to 2. On the previous page, I stated it for D larger than or equal to 3. The theorem, if you interpret it correctly, also holds when D is 2. When D is 2, what can be happening, or what has to be happening, if the degree is 2, we think about these equations, these xi's to the p to the e have degree p to the e, and these xi's, of course, have degree 1. So if I want this product to have degree 2, I'm forced to have p to the e to be 1, which means I'm essentially forced to have e to be 0. So in that case, if e is 0, I can allow p to be anything, and I have a quadric. And this is, in some sense, a generalization of the theory of quadrics. Maybe you remember from long ago algebra qualifying exam for a PhD program that quadric polynomials, homogeneous quadratic polynomials can be written in a matrix factorization like this, and we know how to classify them. So this is now not quadrics, much bigger degree, but the same thing. Now this also holds in characteristic 0, it turns out, when D is 2, because then I can let P be 0 as long as I interpret 0 to the 0 as 1. All right, so that is an alternate form of our theorem. It gives a very nice algebraic description of the polynomials that define a hypersurface, which is the maximally possible singularity we could have. And we can even do more with this. We can classify completely all the singularities, the extremal singularities. So here I'm just showing you an example. If I have an extremal singularity, for example, in 4 variables, so this would be a hypersurface in 4 space with a singularity at the vertex. So it's a 3D shape with a singular point. This thing is, if it's extremal, we know it can be factored in this form for some 4 by 4 matrix. Now, every such hypersurface, when I change coordinates, will have to be one of the ones on this list. So there's only 5 isomorphism classes of these things. And in fact, there's only one right here with an isolated singularity. And these are all of them. And in general, for any number of variables and any degree, we can classify the extremal singularities in a similar way. There's a similar pattern for writing down matrices, and they correspond bijectively to partitions of n if we're working in n variables. So that's an interesting classification theorem. And this is closely related. It might look familiar to some people who have studied Hermitian forms. It's not exactly what we're doing, but in some ways, some of the same ideas are coming up. And when we start looking into, it looks like a very rich area. Many people have stumbled onto related things, counting those kind of matrices for different reasons and so forth. And here I've just put a list of some of them. And actually, this goes all the way back to the 1800s. There's a paper of Haas and Witt. It's actually counting something slightly different than what we are, but with the same count. So there's a bijection between the things we're counting. So this is a very rich topic that we stumbled into kind of serendipitously, and it's been great fun. Okay, so I have described for you a algebraic description of extremal singularities. Now I want to talk about a geometric description of extremal singularities. So for this, I'm going to start by just taking the cone over a smooth cubic surface. So a smooth cubic surface, here's a picture of one of them. It is defined by one polynomial in 3 variables. So we're looking at a surface in 3 space. And let's take a smooth surface in 3 space for fixing the ideas and build the cone over it like we did before. We build the cone over it. We're going to have an isolated cone singularity. It's going to be in 4-dimensional space. It'll be a 3-dimensional object in a 4-dimensional space, and it will have an isolated singularity at the vertex of the cone. So we actually can describe exactly which one of those cone singularities are extremal in terms of the 27 lines on the cubic surface. So this is a beautiful classical theorem. It's not my favorite theorem because I told you Hironaka's theorem is, but I love this theorem as well. Every smooth cubic surface, of course, the people studying this were thinking of complex surfaces, but this is true over any field. Any smooth cubic surface contains exactly 27 lines. Here's a picture of one, and you see 27 lines. It doesn't, they're not all cubic surfaces are isomorphic. In fact, there's a very large parameter space of them, different isomorphism types, but all of them will have exactly 27 lines on them. And we can say exactly when the cone over a cubic surface is an extremal singularity in terms of the configuration of these 27 lines. So I want to explain how. I think it's really beautiful. So let's take our cubic surface. Now we're just thinking about the smooth cubic surface. Of course, the singularity we're interested in is the cone over it. But for a moment, focus on that cubic surface. Concrete thing sitting in the 3-dimensional space. If I intersect it with a random plane, such as, say, the XY plane, just intersect it, what I'm going to get is going to be the intersection will be a cubic curve. It will be defined by a polynomial now in 2 variables instead of 3 variables in that plane. So I'll get the intersection of my cubic surface with a random plane will give me a cubic curve in the plane. So here I drew a couple of possibilities that you might get. For most of the intersections, if I just take a totally random plane, nothing special about its configuration with the surface, I'm going to see a smooth curve as the intersection. This purple curve here is the intersection of X with the plane lambda. But for some special planes, specifically for planes that are tangent to the surface, I will get a singular curve. So that alpha curve is a degree 3 curve. It could come up as an intersection of the cubic surface with a plane. So it's a smooth cubic surface, but some of these plane sections are singular. And if I'm tangent at 2 points, I will get 2 singular points. And so I have a cubic which will have 2 singular points. For example, it could be a union of a degree 2, like a circle and a line. That's a degree 3 plane in the curve with 2 singularities. So it can have more than one component. And in particular, sometimes we would have 3 tangents. The plane might be tangent at 3 points, or it could be tangent at 1 point with a multiplicity 3 intersection. And so sometimes this plane, when we intersect it with a cubic surface, we'll get a union of 3 lines. This happens for very special planes. And in fact, we know exactly how many. I'll come to that in a minute. I just wanted to show you this beautiful picture that Dave Mador let me use, that he created when he wrote his thesis. So this is a picture of a cubic surface. And for example, if I take this point on the cubic surface, that's the intersection of 2 lines. And when I look at the plane spanned by that point and see where it intersects the plane, I'm going to get something. This is a not very good picture, but a picture of it looks supposed to be the cubic surface with the 3 lines on it. So the intersection of one of those points, the plane that contains those 2 lines intersecting at that point that plane intersection with the cubic surface will be a triangle. But if I take this pink point here, I will get a star-like object, like we saw before. So these kinds of intersections of cubic surfaces have been pretty well known, at least for the complex numbers, for almost 2 centuries. We know that there's exactly 45 planes where we get the 3 lines. And almost always, if I just take a totally random, a generic cubic surface, I won't have any stars. I'll only have triangles. And so this is kind of what we usually expect. Getting a star is special, and it happens rarely. It does happen, for example, for this surface, which is called the Klebsch surface, by the way. What we proved is that we can tell when we have an extremal singularity. So the cone over a cubic surface, a smooth cubic surface, is an extremal singularity. So that's, again, an isolated 3-dimensional order 3 singularity, if and only if there are no triangles. Each and every one of those 45 planes intersecting in 3 lines gives us a star. It's amazing. This never happens over the complex numbers. It's been well known for a pretty long time that over the complex numbers, there's at most 18 of those 45 planes with 3 lines in them that will be star points like this. These are also called Eckert points because Eckert had studied these carefully. So that is our theorem in that special case of cubic surfaces, where the cone over a cubic surface. And I wanted to point out that a similar thing describes the cone singularities in general. So I'm not going to state the most general theorem, but let's just stick again to cones over a smooth surface, but not necessarily anymore a cubic surface. So if I take a smooth surface of degree d, so again, this is just a surface in a 3D space, and it's nice and smooth, and it's cut out by a degree d polynomial. And then I take the cone over it. The cone over it will be also a hypersurface, but it will be in now 4 space, cut out by a homogeneous degree d polynomial. It has an isolated singularity at the vertex of the cone, at the origin. And that singularity is an extremal singularity. It has the minimal possible singularity index for its degree. Essentially, if and only if all plane sections where we see lines are stars. So if I take a line on that surface and I take another line on that surface that intersect and I look at the plane they span, I will see a star. The star will have to be d lines crossing at a point, because in general, when I take an intersection of this degree d surface with a plane, I will have a degree d curve. And so this is what happens. This doesn't happen again for complex surfaces, but it can happen in special characteristics P. These are the extremal surfaces. So with my collaborators here, Janet and Tim are postdocs at the University of Michigan, soon moving to the University of North Dakota. Great catch for them. And Anna Brosowski is a PhD student at Michigan. We proved many things about these extremal surfaces, we call them. The surfaces, smooth surfaces, whose cone over them is an extremal singularity, including the things you see on this list and some other things. So let me now end with an open question. I tried to put at least one open question in each talk. And this, I think, is an interesting one. So these extremal surfaces that we've been talking about have surprisingly, almost shockingly many lines on them. So let's just think classical geometry for a moment, going back to the 18 and early 1900s. People were very interested in studying smooth surfaces in 3 space. and looking at how many lines they can have. So we know if we have a cubic surface, we have exactly 27 lines. If I have a quartic or a quintic or a higher degree surface in 3 space, in general, it won't have any lines. However, some special ones do have some lines, and people have been interested in bounding the maximal possible number of lines you can have on a degree D smooth surface in 3 space. And there is a known quadratic bound. It has been known in quotes, maybe in the 18 and 1900s. It has been rigorously proved more recently in this century, and a very precise formula has been given. And this is for surfaces over the complex numbers. There's a quadratic bound in D. Now, if you look back at our theorem has a nice smooth surface with D4th, roughly, degree to the 4th lines on it. That's a lot more lines than we should expect to see. And so an extremal surface is, again, something that can only happen in characteristic P. That's where the singularities are the worst. It's also where you can have the most lines, as it turns out. We think, we haven't shown it yet, that is an absolute bound. Our number of lines on an extremal surface, we counted the exact number. We don't think there's any surface with more lines. Maybe I just have a lot of optimism in these extremal things, but it feels like we would like to prove that someday. And let me point out that Bauer and Rams, who did some of the most recent work on this bound and have improved it and corrected errors in earlier papers and so forth, they have a quadratic bound for large D relative to the characteristic. So RD is small relative to the characteristic. So this is, in any case, a theorem that a question that I want to ask. Is there a smooth surface that has more than this many lines on it? So with that, I will end and thank everybody very much for coming to my talks, and take any questions that might arise.
Okay, so on behalf of the whole audience, let me thank you for 3 really beautiful talks. I thoroughly enjoyed them, and I'm sure many other people did as well. I don't at the moment see any questions in the Q&A. Oops, something just appeared. Just hold on a second here. It says, thank you so much for your talks. Are extremal surfaces isolated in the space of degree D surfaces?
If I understand the question, I think so, because up to isomorphism, there are only finitely many. So you're thinking about a moduli space of degree D surfaces, and then looking at the extremal surfaces there, there's only finitely many. So yes, if I understood the question correctly.
So does this, I'll ask, does this moduli space make sense for in the finite field case, or only in a complex?
Yeah.
You can think of it as a moduli space?
Everything makes sense over arbitrary field. Yeah.
Right.
Yeah.
Okay, we have another question. Just to clarify, when D is not P to the E plus 1, is it true that your result shows there is no surface achieving the bound 1 over D minus 1?
Yes.
Yeah. And if
the
so,
answer is
sorry.
Yes.
Okay. And it says, if so, is it known whether the bound is nevertheless sharp?
Well, I guess it wouldn't be sharp because, well, I mean, I don't know the answer exactly. I don't know a lower bound better than this one for curves of degree D that are not where D is not P to the E plus 1. Does that answer the question? It's hard to maybe what does answer live mean? Can I click on that and will something happen? Anyway,
actually.
Yes, it does.
It does.
Okay.
Oh, what's
Oh, yes, it does answer the question. I think that's what he means.
Okay.
Yeah. So, yeah, we don't have a bound. I mean, this is an interesting problem. Prove one. Maybe there's a better bound. I don't know if it's sharp in the sense that it's sharp when you look at all surfaces, but if you fix a D and look, I don't know. I suspect it is not. I suspect that there are better bounds if you avoid p to the e plus 1. P to the e minus 1, maybe you can find one there. That's a better bound.
Any other questions? Well, I'll just read out a comment from Barbara Kiefitz, who says, no questions, but this was a wonderful series of talks, and I would certainly agree with that.
Thank you.
So
thank you for listening
wait a
and
minute,
for your
wait a minute,
patience with all of the technical difficulties, including my own bouncing back and forth from slides and having trouble with the
There's
Zoom.
one more question that just appeared. Hold on.
Okay.
Oh, wait. Oh, no, two. I'm sorry. Sorry, a couple more questions. Is the singularity index local? Or if I have multiple singularities on a variety, is there some relation among them?
Yes, the singularity index is definitely local, and it's lower semi-continuous. It sounds like it's an algebraic geometer asking that question. Yeah, yes, it is local. So it makes sense even at non-closed points, and it is lower semi-continuous. So I can see this question. Doug Lind wants to know if I read the original proof, and the answer is no. I did try, and I have not, but I have read Janos Kohler has a shorter proof, and I have read that. But it is something I take as gospel. I don't know the details of it. I could not give you the proof right now.
That's great.
It's a valid point.
200.
By the way, people often, sorry?
It says the proof was 250 pages long. That's what the comment says.
I think that's true. It did span 2 volumes of annals. I don't remember exactly how many pages, but I'm sure that's reasonable, in the right ballpark.
Wow. Okay.
And we'd like to have a proof of it in characteristic P as well. I believe it, but we don't have a proof.
All right.
Sometimes there are claims of proofs, and maybe there's even some correct proofs right now brewing, but I don't want to say any more because I don't know the status of any of them.
Okay, well, it looks like that's it. So let's thank Karen one more time. I'll clap for everybody in the audience.